For most of human history, life was dangerous, uncertain, and painfully hard. Hunger was common, infection was frequent, injury could end a life quickly, and yet the human body was shaped inside that harshness, refined by scarcity, movement, cold nights, and constant risk. Today, many of us live longer, eat more, move less, and survive threats our ancestors could not imagine. And strangely, as life becomes safer and easier, chronic disease quietly spreads. How did a body built to endure difficulty begin to weaken in comfort? For most of our existence, the human body did not wake to silence, climate control, and steady light. It woke to uncertainty. The air was colder before dawn. Hunger was never far away. Movement began early, not as exercise, but as survival. To understand why humans get sick when life gets easier, we have to return, slowly and carefully, to that beginning. The first humans did not live in comfort long enough for comfort to shape their biology. Their bodies were calibrated in a world where energy had to be earned daily. Muscles were not optional. Walking long distances was ordinary. Carrying, climbing, crouching, and lifting were woven into each day. In that environment, blood sugar rose and fell with effort. Food did not arrive predictably. Periods of eating were followed by natural pauses, sometimes forced by scarcity. Over thousands of generations, the body learned to respond to this rhythm. Hormones adjusted to fluctuation. Cells adapted to cycles of use and recovery. The immune system matured in constant contact with soil, animals, plants, and other humans. Exposure was not a choice. It was a condition of being alive. Cuts, parasites, microbes in water and food, these were common encounters. The immune system did not live in isolation. It trained continuously, responding, correcting, and remembering. In such a setting, inflammation was often brief and purposeful, activated by injury or infection, then resolved. The body expected challenge. It expected movement. It expected variation in temperature, light, and food supply. Even sleep followed the sun more closely. Artificial light did not extend the day far into the night. Darkness was longer and deeper. The nervous system learned to calm in extended darkness and to mobilize at first light. The original human environment was not healthy in a modern sense. Infant mortality was high. Infections could be fatal. Injuries could not always heal. Yet the body systems that evolved in that world were designed for acute threats, not for constant surplus. When a predator appeared, stress hormones surged and then fell. When food was scarce, metabolism shifted to preserve energy. When injury occurred, inflammation rose and then retreated. These systems were dynamic, flexible, and temporary. The key detail is that difficulty was intermittent but unavoidable. It came in waves. The body was shaped by repeated cycles of strain and recovery. Over time, genes that supported survival in scarcity were favored. The ability to store fat efficiently during times of abundance became an advantage. The capacity to mount a strong inflammatory response to infection improved short-term survival. The sensitivity of the stress response system increased alertness in dangerous settings. These traits were not flaws. They were solutions to a world where danger was immediate and resources were unstable. In that long prehistoric landscape, life was physically demanding but biologically coherent. The signals from the environment matched the expectations encoded in the body. Movement matched muscular design. Variable food intake matched metabolic flexibility. Microbial exposure matched immune development. Darkness matched circadian rhythm. When we ask why humans get sick when life gets easier, we are not comparing health in a moral sense. We are comparing environments. The early human body evolved under pressure, shaped by scarcity, exposure, and unpredictability. It did not evolve in a climate-controlled room with unlimited calories and minimal physical strain. The mismatch begins when the signals from the environment no longer resemble the conditions that formed the body in the first place. To understand illness in a comfortable world, we must first understand the world in which the human body learned what normal meant. The early human body did not simply endure difficulty, it depended on it. Effort was not an interruption to health, but part of its maintenance. When we look back toward the long stretch of time before cities, before agriculture, before permanent shelter, we see a pattern that repeats quietly: strain followed by recovery. This rhythm shaped internal systems in ways that are easy to overlook in a world where strain can be optional. Movement was rarely concentrated into short bursts. It was spread throughout the day. Walking in search of food, tracking animals, gathering plants, carrying children, shaping tools, preparing firewood. Each action required muscle contraction and energy use. The heart and lungs were engaged regularly, not to improve fitness, but to meet necessity. In that setting, circulation was not stagnant. Blood moved through active tissue. Glucose was taken up by working muscle. Insulin rose and fell in response to real demand. The metabolic system expected use. Without use, it had no clear signal for how to behave. At the same time, food was uneven. Some days offered abundance after a successful hunt or a rich harvest of seasonal fruit. Other days brought less. This variability created natural cycles of energy surplus and energy deficit. During short periods of lower intake, the body shifted towards stored fuel. Fat was mobilized. Cells increased efficiency. Repair processes that depend on energy balance were activated. These shifts were not extreme starvation, but ordinary fluctuations that signaled to the body that resources were never guaranteed. Over thousands of generations, these cycles became part of biological expectation. The immune system, too, matured within constant interaction with the surrounding world. Soil carried bacteria. Animals carried parasites. Water was not sterilized. Exposure began early in life. Children encountered microbes through touch, through shared space, through unfiltered air. The immune system learned by practice. It distinguished between harmless organisms and dangerous ones not in isolation, but through repeated contact. This training helped regulate inflammatory responses. Activation was frequent but usually resolved when the threat passed. The nervous system followed a similar pattern of activation and release. Acute stress was common. A sudden sound in the dark, a potential predator, a conflict within the group, these triggered rapid mobilization. The heart rate increased. Attention sharpened. Muscles prepared for action. Yet these moments were often brief. Once the danger ended, the body returned to baseline. Darkness signaled rest. Social closeness signaled safety. There was little prolonged mental anticipation of distant threats. Stress was physical, immediate, and usually short-lived. Even temperature played a role. Early humans experienced cold mornings and warm afternoons. Fire offered relief, but climate control was incomplete. The body adjusted through subtle metabolic changes, through brown fat activation, through shifts in circulation. Variation was normal. Constancy was rare. When we observe these elements together, movement, variable food intake, microbial exposure, intermittent stress, temperature shifts, we see a pattern of controlled instability. The body was never static. It was always responding. This responsiveness became its strength. Health, in that context, did not mean absence of hardship. It meant adaptability within hardship. The difficulty of life acted almost like a tutor, reinforcing systems that relied on challenge to remain balanced. The crucial detail is that these pressures were woven into daily existence from the beginning of our species. They were not occasional lifestyle choices. They were the environment itself. As life becomes easier, many of these signals fade. Movement decreases. Food becomes constant. Microbial exposure narrows. Stress changes form, becoming psychological and prolonged rather than acute and physical. Temperature stabilizes. Light extends into the night. The body, still shaped by ancient rhythms, continues to expect fluctuation. When fluctuation disappears, regulation may change in ways that are subtle at first. To understand sickness in a comfortable world, we must keep returning to this original pattern. A body built not for steady ease, but for responsive adaptation within ongoing challenge. If we slow down even further and look at the span of time involved, another detail becomes impossible to ignore. Anatomically, modern humans have existed for roughly 300,000 years. For more than 95% of that time, daily life followed the patterns we have just described. Movement as necessity, food as variable, exposure as constant, darkness as real, permanent settlements, large cities, artificial lighting, processed food, and climate control occupy only a thin edge of that timeline. In evolutionary terms, it is a narrow sliver at the end. The body we carry today is almost identical, in structure and basic physiology, to the bodies that moved across African savannas and later into forests, coastlines, and cold northern plains. Bones, muscles, organs, and hormonal systems did not redesign themselves in the last few thousand years. Natural selection works across long spans, and while small genetic adaptations have occurred in some populations, the overall architecture remains rooted in that earlier world. This is important because it defines what the body recognizes as normal. Normal, in a biological sense, is not what is common today. It is what was common during the long period when survival determined which traits persisted. When energy was scarce, the ability to store fat efficiently increased the chance of surviving famine. When infections were frequent, a strong and rapid inflammatory response increased the chance of surviving wounds. When danger could appear suddenly, a sensitive stress response improved vigilance. These traits were not designed for comfort, they were designed for survival in uncertainty. From the perspective of archaeology, we can see evidence of active lives in skeletal remains. Bones from early human populations often show signs of repetitive loading, muscle attachment patterns that reflect frequent use, and joint wear consistent with constant movement. At the same time, evidence of healed injuries tells us that recovery was possible, that strain was balanced by repair. The body endured stress but also adapted to it. There was no long period in which inactivity became the norm. When we move forward through time and approach the present, the contrast becomes sharper. In only a few centuries, and especially in the last 100 years, daily energy expenditure in many societies has declined dramatically. Food has become abundant and continuously available. Artificial light extends the waking day. Medical advances reduce mortality from acute infections. These changes represent extraordinary achievements, yet they alter the signals that once guided biological regulation. The body still carries metabolic pathways tuned to scarcity. It still maintains immune responses tuned to frequent microbial contact. It still activates stress hormones in response to perceived threat. But the environment providing those signals has shifted faster than the body can adapt. When we say that humans get sick when life gets easier, we are not suggesting that hardship is desirable or that modern progress is a mistake. We are recognizing a temporal imbalance. The biological system was calibrated across hundreds of thousands of years under one set of conditions. The modern environment has changed many of those conditions within a few generations. Evolution does not move at the pace of technology. The question that quietly emerges from this long view is not whether life is better now in terms of safety or longevity. It is whether the internal expectations of the body still align with the external realities of daily life. When those two drift apart, regulation may falter in ways that are not immediately dramatic but gradually accumulate. The seeds of modern illness may not lie in a single behavior or a single nutrient, but in the widening gap between ancient design and recent comfort. In the earliest human landscapes, scarcity was not an occasional crisis. It was a quiet background condition. Food could be found, but not always in abundance, and never with certainty. This uncertainty shaped the metabolism long before written history began. To understand why humans get sick when life gets easier, we must look closely at how the body learned to function when energy was limited and unpredictable. The human metabolism is remarkably flexible. It can use glucose from recent meals, glycogen stored in the liver and muscles, and fat stored in adipose tissue. This flexibility did not appear in a world of constant supply. It emerged because supply fluctuated. A successful hunt might provide ample calories for a short time. Days later, intake might drop. In these shifts, the body adapted not only to survive, but to operate efficiently across changing conditions. When food intake decreased, insulin levels fell. Fat was mobilized to provide energy. The liver produced glucose to support the brain. Muscle tissue adjusted its fuel use. These transitions were not signs of pathology. They were normal responses to ordinary variation. The body was accustomed to moving between fed and fasting states without prolonged surplus. Over thousands of generations, this pattern reinforced genes that favored energy conservation. Individuals who stored energy effectively during abundance were more likely to survive lean periods. Fat storage, therefore, became a protective trait. It was not a flaw, it was insurance. In an environment where famine could follow abundance, the ability to accumulate reserves increased survival odds. This biological logic still exists within us. The difficulty arises when abundance becomes constant. When food is always available and rarely requires physical effort to obtain, the cycles that once defined metabolic rhythm become compressed or disappear. Insulin remains elevated for longer periods. Fat storage pathways are repeatedly activated without corresponding periods of depletion. The body, still expecting variability, continues to store energy as if scarcity might return. From an archaeological perspective, we see signs of nutritional stress in early agricultural societies, but even then, caloric intake was often tied to harvest cycles. Seasonal variation influenced diet composition and quantity. Hunter-gatherer groups that survive into recent centuries often display a similar pattern. Energy expenditure is high and intake varies. Long-term overnutrition, as seen in many industrialized societies, is historically rare. The metabolic system evolved in an environment where surplus was temporary and physical effort was continuous. In that context, short bursts of abundance did not destabilize the system because they were balanced by future demands. The body was not exposed to sustained excess without movement. It did not experience decades of consistent caloric surplus combined with reduced energy expenditure. Scarcity, in this sense, acted as a calibrator. It kept regulatory systems responsive, hormones adjusted, cells adapted, repair mechanisms activated during energy shifts. The alternation between use and rest, between intake and depletion, preserved balance. As life becomes easier and food becomes reliably abundant, this calibration changes. The signals that once guided metabolic flexibility become muted. The body remains equipped for a world where food might disappear tomorrow. Yet tomorrow rarely brings absence. It brings another meal. The tension between ancient expectation and modern constancy begins here, not as a sudden failure but as a gradual divergence. When the body's design assumes scarcity and the environment supplies surplus without interruption, regulation may shift in ways that are subtle at first but meaningful over time. Scarcity did more than shape how the body stored energy. It shaped how the body repaired itself. When food intake fluctuated and physical effort was unavoidable, cells were not only consuming fuel, they were constantly adjusting to stress. Small stresses, cold mornings, long walks, minor injuries, brief hunger, created signals inside the body. These signals activated repair pathways that maintained resilience. In modern biology, this process is sometimes described through the idea that mild stress can strengthen systems when it is followed by recovery. In early human life, such mild stress was not a deliberate practice. It was simply the condition of living. When energy intake dropped for a period, the body did not shut down. It shifted. Certain cellular processes that depend on high nutrient availability slowed. Others associated with maintenance and efficiency increased. Proteins were recycled. Damaged components were broken down and replaced. This was not an extreme response to starvation, but a regular adjustment to variation. Because these cycles repeated across a lifetime, the body became accustomed to periodic recalibration. Movement contributed to this process as well. Repeated muscle use generated microscopic damage in tissue. During rest, that tissue repaired and strengthened. Bones responded to loading by increasing density. The cardiovascular system adapted to repeated demand. None of these adaptations required conscious training programs. They were built into survival. The environment provided the stimulus. The body responded with repair and growth. Over time, this pattern created a close link between challenge and maintenance. The body expected to be used. It expected to experience controlled strain. Without it, certain signals diminished. The immune system followed a similar principle. Minor infections and microbial exposures triggered responses that, once resolved, left behind memory and regulation. The immune network learned through engagement. In an environment where contact with soil, animals, and diverse microbes was routine, immune activity was frequent but often balanced by resolution. Chronic inactivity of this system was rare. It had work to do. When life becomes easier and many of these mild stresses decline, the body does not immediately fail. it continues to function, but the pattern of stimulation changes. Constant comfort can reduce the variability that once signaled cells to adapt. Nutrient abundance may keep certain growth pathways active for long periods. Low physical strain may reduce the mechanical signals that maintain bone and muscle. Highly controlled environments may limit microbial exposure that once shaped immune tolerance. The key is not that stress itself is healthy, but that the body evolved in the presence of manageable recurring challenges. In early human history, recovery followed strain. Nights were dark and long enough for rest. Food variability created metabolic shifts. Movement created structural adaptation. The system operated as a cycle. When we compare this to many modern routines, continuous access to food, extended sitting, artificial light at night, we see fewer natural transitions. The body still carries mechanisms designed to respond to fluctuation. When fluctuation diminishes, the signals for repair and recalibration may also change. This does not mean that comfort directly causes disease in a simple way. It means that biological systems tuned for rhythm may respond differently when rhythm becomes flat. Scarcity, in its original context, was not purely deprivation. It was a teacher that kept repair systems active. As that teacher fades, the body must interpret a quieter environment with tools shaped in a noisier past. Scarcity also shaped perception. It did not only train muscles and metabolism, it influenced how the brain evaluated the world. In early human settings, the availability of food and safety was never guaranteed for long. This uncertainty required constant awareness, but it also established a deep connection between effort and reward. Energy was acquired through movement, cooperation, patience, and skill. The brain's reward systems evolved within this framework. When effort led to food or safety, chemical signals reinforced those behaviors. Dopamine pathways did not respond to abstract achievement or endless stimulation. They responded to tangible survival outcomes. This alignment between physical exertion and reward created a balanced loop. Effort consumed energy. Success restored it. Rest followed action. Even social bonding was tied to shared struggle, hunting together, gathering together, defending together. Emotional satisfaction was embedded in survival tasks. Scarcity, therefore, structured not only the body but the rhythm of motivation. When energy intake was uncertain, the brain became sensitive to cues of opportunity. Sweetness signaled calories. Fat signaled dense energy. Novelty signaled potential resources. These sensitivities were adaptive. They guided attention toward what increased survival chances. Over time, natural selection favored individuals whose brains quickly detected and pursued high-value resources. In a world of limited access, this heightened sensitivity was beneficial. It encouraged efficient decision-making. It reinforced persistence during difficulty. However, the same neural sensitivity that once helped secure rare calories now operates in environments where those calories are abundant and engineered to stimulate desire. The reward circuits have not been redesigned. They still respond strongly to signals associated with energy and novelty. When life becomes easier and high-calorie food is continuously available without effort, the ancient link between work and reward weakens. The brain receives repeated signals of success without corresponding expenditure. This can alter patterns of behavior gradually. At the same time, scarcity influenced stress perception. In early environments, threats were concrete and immediate. A predator, an approaching storm, a rival group, these activated rapid responses that subsided once the event passed. Anticipatory worry about distant possibilities was less relevant than immediate action. The nervous system cycled between activation and rest. When the threat ended, physical exhaustion often followed, encouraging sleep and recovery. In contrast, modern environments often present abstract stressors, financial concerns, social comparison, information overload. These activate similar biological pathways but may persist without physical resolution. The brain, shaped by scarcity and acute danger, interprets signals in a world where threats are less visible yet more constant. The mismatch grows subtle but persistent. Looking back across evolutionary time, we see that scarcity structured expectation. The body expected effort before reward. It expected fluctuation before stability. It expected challenge before rest. These expectations became embedded in hormonal cycles, neural circuits, and metabolic pathways. When life grows easier and many challenges become optional or removed, the signals that once coordinated these systems change. The brain still seeks cues of value. The body still prepares for fluctuation. Yet the environment supplies continuous access and continuous stimulation. Scarcity once aligned survival, motivation, and physiology into a coherent system. When abundance becomes the norm, that coherence may shift. The question quietly emerging is not whether abundance is harmful in itself, but how systems shaped by long periods of unpredictability respond when unpredictability fades and ease becomes constant. For most of human existence, people did not live in permanent settlements. Groups moved across landscapes following seasons, animal migrations, and plant cycles. Camps were temporary. Waste dispersed naturally. Population density remained low. In this context, infectious disease behaved differently from what we recognize today. To understand why humans get sick when life gets easier, it is necessary to examine the moment when mobility slowed and settlement began. The transition to agriculture, beginning roughly 12,000 years ago in several parts of the world, marked a profound ecological shift. Instead of moving with the land, humans began to reshape it. Crops were planted in fixed fields. Animals were domesticated and kept close to human dwellings. Storage of grain allowed larger populations to survive through winter or drought. Villages formed. Over time, villages grew into towns. This change increased stability and food supply for many communities. Yet it also altered patterns of exposure, nutrition, and disease. When humans lived in small, mobile bands, infectious agents had limited opportunity to circulate continuously. A pathogen that depended on close contact might fade out if too few hosts were present. Mobility dispersed waste and reduced long-term contamination of water sources. With settlement, these dynamics shifted. Higher population density created more consistent chains of transmission. Stored food attracted rodents and insects. Domesticated animals lived in closer proximity to people, allowing microbes to cross species barriers more easily. Archaeological and historical records show that many infectious diseases associated with dense populations emerged or expanded after the rise of agriculture and urbanization. This does not mean that early humans were free from disease. Parasitic infections, injuries, and localized outbreaks existed long before farming. But the ecological context changed when humans concentrated themselves and their animals in fixed spaces. The immune system, shaped in a world of dispersed exposure, encountered new patterns. Instead of brief, localized contact, it faced repeated exposure within crowded settlements. Over generations, human populations adapted in various ways. Some genetic traits that confer resistance to certain infections became more common in specific regions. Yet these adaptations occurred gradually and unevenly. Agriculture also altered diet. Instead of diverse wild plants and animals, many communities relied heavily on a few staple crops such as wheat, rice, or maize. Skeletal evidence from early farming populations often reveals changes in stature and dental health compared to earlier hunter-gatherers. Diet became more predictable but sometimes less varied. Periodic famines still occurred when harvests failed, yet between famines caloric intake could be more stable than in mobile foraging groups. The key shift here is not simply that agriculture introduced hardship, it introduced a different type of stability. Humans began to experience longer periods of sedentary life. Work became repetitive. Fields required seasonal labor but less daily long-distance travel. Social structures grew more complex. The environment became increasingly human-made. As life grew more organized and predictable, the relationship between body and landscape transformed. This was one of the earliest large-scale moments when easier in certain dimensions, more reliable food, shelter, and community coexisted with new patterns of illness. The body, evolved in mobility and variation, entered a world of concentration and continuity. The seeds of mismatch were not yet modern, but they were visible. The question deepens. When stability increases, what new pressures quietly emerge in its place? As settlements grew larger and more permanent, another shift unfolded quietly within the body. The change was not only ecological but structural. Daily movement patterns narrowed. Instead of covering wide distances across varied terrain, many people began to work within fixed boundaries: fields, workshops, homes. Tasks were still physically demanding, yet they became repetitive. The diversity of motion that once engaged the entire musculoskeletal system gradually reduced. Archaeological evidence from skeletal remains in early agricultural societies shows changes in bone density, joint wear, and posture. Certain bones thickened in response to repetitive labor, while others displayed signs of strain linked to specific tasks. This suggests that the body was adapting not to varied, natural movement, but to concentrated, specialized effort. Specialization extended beyond physical labor. Social roles became more defined. Some individuals farmed, others crafted tools, others managed storage or trade. With specialization came social stratification. Not all members of a settlement experienced the same physical demands or nutritional access. Differences in diet and workload began to appear within the same community. Skeletal studies often reveal variation in health markers between social classes, indicating that stability did not distribute benefits evenly. From a biological perspective, the immune system also encountered new rhythms. In dense settlements, infections did not always disappear after brief outbreaks. Pathogens could circulate continuously. Children, in particular, were exposed at younger ages to a broader range of microbes within confined spaces. While this repeated exposure sometimes strengthened immunity, it also increased the burden of infectious disease. Over time, human populations developed partial resistance to certain pathogens, yet this process unfolded across generations. Meanwhile, malnutrition could weaken immune defenses, especially when diets relied heavily on a single staple crop lacking certain micronutrients. The shift to grain-based diets, though efficient for feeding large populations, often reduced dietary diversity compared to foraging patterns that included varied plant and animal sources. Dental remains from early farming communities frequently show higher rates of cavities and enamel defects, reflecting increased carbohydrate consumption and periodic nutritional stress. The body, which had evolved to handle fluctuating but diverse intake, now encountered sustained reliance on fewer food sources. This change did not immediately create modern chronic diseases, but it altered metabolic and immune landscapes. Another subtle transformation involved waste accumulation. In mobile groups, waste dispersed naturally across the landscape. In settlements, waste gathered near living areas unless managed deliberately. Contaminated water sources and close proximity to domesticated animals increased exposure to pathogens. These were not abstract risks, but daily realities. The environment that humans had shaped to provide stability introduced new microbial pressures. In this period, life in some ways became more predictable. Food storage reduced certain forms of uncertainty. Community offered protection. Yet the concentration of humans, animals, and waste created ecological conditions unfamiliar to a body designed for dispersed living. The ease of stable settlement carried hidden costs. It reorganized movement, diet, exposure, and social structure in ways that slowly diverged from the long evolutionary baseline. The pattern begins to take shape. Each step towards stability introduces a new configuration of challenges. The body continues to respond, but always within constraints set long before cities and farms existed. As generations passed within agricultural societies, the consequences of settlement did not remain confined to infection and nutrition. They extended into patterns of survival and population structure. When food production became more stable, even if imperfect, more children could survive infancy. Communities grew. Lifespans in some regions gradually increased, not because the human body had fundamentally changed, but because external conditions allowed more individuals to reach adulthood. This demographic shift altered the balance between acute and chronic pressures. In small mobile bands, high mortality from injury or infection limited the number of individuals living into later decades of life. In larger, settled populations, even with ongoing disease, more people survived long enough to experience the cumulative effects of aging. The body, still shaped in an era where few individuals reached advanced age, now had to function across longer spans, under new environmental conditions. The stresses of repetitive labor, limited dietary diversity, and persistent infection accumulated over time. Skeletal remains from early cities often show signs of chronic joint degeneration. spinal compression, and nutritional deficiencies. These are not modern chronic diseases in the form we recognize today, but they reveal a pattern. When stability increases lifespan and population density, the body begins to carry long-term burdens more visibly. Another change involved social proximity. Dense settlements encouraged close, sustained interaction among unrelated individuals. This supported cooperation and cultural development, yet it also facilitated the spread of respiratory and gastrointestinal infections. Over time, certain diseases became endemic, persisting within populations rather than appearing as isolated outbreaks. The immune system, originally shaped for episodic contact within small groups, adapted to a new ecological rhythm. Yet adaptation at the population level did not eliminate disease. It often meant that infections became a regular part of childhood experience. The concept of normal illness shifted. Agriculture also introduced cycles of surplus and famine on a larger scale. When harvests succeeded, stored grain supported population growth. When harvests failed, entire regions faced starvation. These boom and bust cycles created oscillations in health at the population level. During famine, malnutrition weakened immune defenses, increasing susceptibility to infection. During surplus, carbohydrate-heavy diets sometimes dominated. The metabolic system, originally calibrated for fluctuating but varied intake, encountered long stretches of dietary monotony. What becomes clear in this long historical view is that ease does not eliminate pressure. It rearranges it. Settlement reduced certain dangers, constant mobility, exposure to predators but concentrated others. Humans traded one pattern of risk for another. The body continued to operate with the same fundamental biological toolkit developed over hundreds of thousands of years. Yet the environment surrounding that toolkit had changed in scale and density. When we look across this transition, we see the early outlines of a pattern that will later intensify in industrial and post-industrial societies. Stability, predictability, and concentration alter exposure, diet, and lifespan. Each adjustment increases the distance between the original evolutionary context and the current one. The shift was gradual and uneven, but it marked a turning point. The human body entered a world increasingly shaped by its own innovations. As living conditions became more organized and, in some respects, easier, new forms of strain emerged, less visible than a predator in the dark, but persistent across years and generations. The deeper question remains, when humans redesign their environment for comfort and stability, how long can a body built for mobility and variation maintain balance within that new design? The transition from agriculture to industry unfolded slowly at first, then with accelerating force. For thousands of years, most humans lived close to the land. Even within settled societies, work remained tied to seasons, daylight, and physical effort. Then, over the course of a few centuries, and especially within the last 200 years, another transformation reshaped the human environment more rapidly than any before it. Machines began to replace muscle. Fossil fuels replaced wood and human labor. Artificial light extended the day beyond sunset. Cities expanded in size and density beyond anything previously experienced. To understand why humans get sick when life gets easier, this acceleration demands careful attention. In industrial societies, the need for constant physical movement declined for large segments of the population. Factory work could be repetitive and exhausting, yet it often involved limited ranges of motion. Later, as technology advanced further, many occupations shifted from physical labor to sedentary tasks. Sitting became common for long stretches of the day. The cardiovascular system, evolved for frequent engagement, encountered extended periods of relative inactivity. Muscles that once contracted regularly to support survival were used less often. Circulation patterns changed. Energy expenditure dropped. At the same time, food production transformed. Industrial agriculture increased yield and efficiency. Food preservation improved. Transportation networks allowed calories to travel across continents. Seasonal variation diminished. Highly processed foods, dense in energy and engineered for shelf stability, entered daily life. For the first time in human history, large populations could access inexpensive, calorie-rich food year-round without direct physical effort. The metabolic system, still tuned to scarcity and fluctuation, now faced sustained surplus. The environment became more controlled. Climate regulation reduced exposure to cold and heat. Indoor plumbing improved sanitation. Antibiotics and vaccines reduced mortality from many infectious diseases. These advances dramatically improved survival and comfort. Infant mortality declined. Life expectancy rose in many regions. Yet as infectious diseases receded in prominence within industrialized nations, chronic diseases gradually emerged as leading causes of illness and death. Conditions related to metabolism, cardiovascular function, and immune regulation became more visible. This shift did not occur overnight, nor was it uniform across the globe. It followed patterns of urbanization, industrialization, and lifestyle change. From a biological perspective, the most striking feature of this period is speed. The agricultural transition unfolded over millennia. The industrial transformation compressed major environmental changes into a few generations. Evolutionary adaptation cannot keep pace with such rapid shifts. The genes that shaped energy storage, stress response, and immune function remain largely the same as they were before factories, electricity, and processed food. Yet the signals that activate these genes have changed dramatically. Artificial light delays melatonin release and alters circadian rhythms. Sedentary routines reduce mechanical stimulation of bone and muscle. Continuous access to food minimizes fasting intervals. Psychological stressors tied to social complexity and information flow become more constant. The body continues to operate according to ancient regulatory principles, but the context in which it operates has been redesigned at unprecedented speed. Ease increases in measurable ways. Safer childbirth, longer lifespans, controlled temperature, abundant calories. At the same time, new patterns of imbalance quietly accumulate. The industrial acceleration does not negate human progress. It reveals the tension between biological inheritance and technological innovation. When change outpaces adaptation, systems shaped in one environment must function in another. The distance between evolutionary design and daily experience widens further. The question deepens: how does a body calibrated over hundreds of thousands of years respond when, within a few generations, the structure of life transforms beyond recognition? As industrialization advanced, another layer of change emerged, less visible than factories or machines, but equally profound. Daily life became increasingly structured around schedules rather than seasons. Time, once guided primarily by sunlight and environmental cues, began to follow clocks. Artificial lighting allowed activity to extend deep into the night. Work shifts divided the day into segments that did not always align with natural circadian rhythms. The body, however, continued to rely on internal clocks shaped long before electricity. The circadian system coordinates sleep, hormone release, digestion, immune activity, and cellular repair. It evolved under a predictable pattern of bright days and dark nights. When darkness fell, melatonin increased, body temperature shifted, and restorative processes intensified. In industrial societies, prolonged exposure to artificial light after sunset alters this sequence. Even moderate light can delay melatonin release. Sleep may shorten or fragment. Over time, irregular sleep patterns can influence metabolic regulation and stress hormone levels. The body remains capable of adapting to occasional disruption, but chronic misalignment introduces subtle strain. The rhythm that once matched the rising and setting sun becomes less distinct. Alongside circadian disruption, urban living reshaped sensory experience. Noise levels increased. Visual stimuli multiplied. Information began to flow continuously through print, radio, television, and eventually digital networks. The nervous system evolved to respond to immediate physical threats or social signals within small groups, now processes abstract concerns and constant alerts. Financial uncertainty, social comparison, global news, these do not resemble a predator in the grass, yet they activate overlapping biological pathways. Cortisol and adrenaline may rise not in brief bursts, but in sustained patterns linked to ongoing psychological stress. Unlike acute danger, which often resolved with physical action, modern stressors may persist without clear physical resolution. This difference alters the stress recovery cycle. In early environments, activation often led to movement running, fighting, climbing. Afterward, exhaustion encouraged rest. In industrial contexts, Stress may occur while sitting at a desk or lying awake at night. The body prepares for action that never fully arrives. Hormonal systems designed for rapid response encounter prolonged stimulation. Over years, this pattern can influence cardiovascular function, immune balance, and metabolic pathways. Industrialization also intensified social stratification and economic specialization. Large urban centers concentrated wealth and poverty side by side. Access to nutritious food, safe housing, and healthcare varied widely. The concept of ease became unevenly distributed. For some, industrial life reduced physical hardship and increased longevity. For others, it introduced crowded housing, pollution, and dangerous labor conditions. The health effects of industrialization were therefore complex, improving survival in certain respects while introducing new forms of exposure and inequality. Air quality changed as well. Burning coal and later oil released pollutants into densely populated areas. The respiratory system, adapted to natural particulates such as dust and smoke from occasional fires, encountered sustained exposure to industrial emissions. The immune system and lungs responded, but long-term exposure carried cumulative effects. When examining this period, a consistent pattern appears. Technological ease and environmental modification alter biological signals. Light extends into night. Food becomes constant. Work shifts away from varied physical activity. Psychological stress intensifies in new forms. The body remains fundamentally the same organism that once synchronized with daylight and moved across landscapes in search of food. Yet it now inhabits a world of mechanical precision and constant connectivity. The tension between ancient biological rhythms and industrial schedules deepens quietly. The question remains open. As life becomes more organized and efficient, how does the internal timing system of the human body adjust, or fail to adjust, to this new architecture of time and space? As the industrial era matured into the modern technological age, another quiet transformation took place inside the human body. Medical advances dramatically reduced mortality from many acute infections. Vaccination campaigns, antibiotics, improved sanitation, and surgical techniques extended life in ways unimaginable in earlier centuries. Infant mortality declined sharply in many regions. People survived injuries and illnesses that would once have been fatal. From a historical perspective, this represents one of the most significant improvements in human survival. Yet survival changes the landscape of disease. When more individuals live into middle and older age, patterns of illness shift. The body, evolved in conditions where many did not reach advanced decades, now operates across longer spans of time. Wear accumulates. Repair mechanisms continue to function, but they must work for far more years than in most of our evolutionary past. Chronic conditions that require time to develop become more visible, not because the body has suddenly weakened, but because it persists longer within altered environments. This demographic extension interacts with industrial conditions in complex ways. Sedentary routines, calorie-dense diets, disrupted sleep cycles, and persistent psychological stress unfold not over short bursts but over decades. The cumulative effect becomes central. Biological systems designed for flexibility under intermittent challenge must now regulate under sustained exposure to novel conditions. For example, low-level inflammation, once a temporary response to infection or injury, may become more persistent in environments characterized by continuous metabolic surplus or chronic stress. In earlier eras, individuals susceptible to certain metabolic or cardiovascular conditions might not have lived long enough for those conditions to fully manifest. Modern medicine allows survival beyond acute crises, revealing vulnerabilities that were previously masked by shorter lifespans. The structure of mortality changes from sudden infectious events to prolonged management of chronic disease. Ease, in the form of medical protection, reduces one category of risk while making another more apparent. Urban infrastructure further intensifies this pattern. Clean water systems reduce waterborne disease. Refrigeration preserves food. Transportation systems ensure supply chains. These achievements reduce immediate threats, yet they also support constant caloric access and reduced physical necessity. The protective environment becomes so stable that biological systems once shaped by variability now operate under near-continuous uniformity. The body is shielded from certain dangers while remaining exposed to others that emerge gradually: excess energy intake, limited movement, sustained stress signaling. Importantly, none of this suggests that industrial or medical progress is inherently harmful. The gains in survival and quality of life are profound. The tension arises from temporal scale. Evolution shaped the human organism across hundreds of thousands of years within one ecological context. Industrial transformation and medical advancement altered that context within a few generations. The internal architecture, metabolic pathways, immune regulation, stress responses remains largely consistent with ancient design. The external environment has shifted dramatically. As the modern age stabilizes many external threats, the pattern of illness reconfigures, acute dangers recede, chronic imbalances become more visible. The body does not fail suddenly under comfort. It adjusts gradually, revealing the limits of systems built for a different tempo of challenge. The essential question lingers without accusation or nostalgia. When protection extends life and reduces immediate hardship, how does a body calibrated for intermittent strain navigate decades of relative stability and continuous exposure to abundance? For most of human history, the immune system developed in constant dialogue with the surrounding world. Soil, animals, untreated water, shared sleeping spaces, and close physical contact created a microbial environment far more diverse than what many people experience today. This exposure was not always benign. Infections could be severe. Parasites were common. Yet from infancy onward, the immune system learned through repeated encounters. It distinguished over time between threats that required strong responses and organisms that could be tolerated. To understand why humans get sick when life gets easier, we must look carefully at what happens when this early training ground changes. The immune system is not a single organ, but a network of cells and signals distributed throughout the body. It includes rapid responders that attack pathogens immediately and regulatory components that calm the response once danger has passed. Balance between activation and restraint is essential. In early human environments, frequent microbial contact stimulated both sides of this system. When exposure occurred, immune cells responded. When the infection resolved, regulatory pathways helped reduce inflammation. This repeated cycle shaped a pattern of responsiveness followed by resolution. In highly sanitized environments, especially those common in industrialized societies, many early life exposures are reduced. Clean water, treated food, antibiotics, and controlled indoor environments limit contact with a wide range of microorganisms. These changes have dramatically reduced mortality from infectious diseases, representing a major public health success. Yet some researchers have proposed that reduced microbial diversity may influence how the immune system calibrates itself. This idea, often described as the hygiene hypothesis, and later refined into broader concepts about microbial diversity, suggests that limited early exposure may alter immune regulation in certain contexts. The evidence supporting this idea is complex and still developing. Studies have observed that children raised in environments with greater contact with farm animals or diverse outdoor settings sometimes show lower rates of certain allergic conditions. However, these patterns vary across populations, and no single factor explains immune-related diseases. What remains clear is that the immune system evolved in partnership with a rich microbial environment. The human body itself hosts trillions of microorganisms, particularly in the gut. These microbial communities assist in digestion, vitamin production, and immune modulation. Changes in diet, antibiotic use, and living conditions can alter this internal ecosystem. In traditional settings, diets rich in varied plant fibers support diverse gut bacteria. In modern diets, lower fiber intake and higher levels of processed foods may reduce microbial diversity. This shift does not automatically cause disease, but it changes the signals exchanged between microbes and immune cells. Over evolutionary time, the immune system expected a certain level of background stimulation. It expected minor infections, environmental microbes, and constant microbial communication. In easier environments where many infectious threats are removed, that background changes. Some scientists explore whether this altered stimulation may relate to increases in allergic and autoimmune conditions observed in certain industrialized populations. The mechanisms remain under investigation, and many variables, including genetics, pollution, and lifestyle, interact in complex ways. What is certain is that ease in the form of sanitation and reduced infection has saved countless lives. At the same time, the immune system continues to operate according to principles shaped long before modern hygiene. When exposure patterns shift rapidly, regulation may adapt in ways that are not always predictable. The broader pattern reappears. Systems evolved under one set of environmental signals now function within another. The immune system, once trained in diverse microbial landscapes, now interprets a more controlled world. How it balances vigilance and tolerance in this new context remains an ongoing question. The immune system does not only defend against external threats, it also participates in ongoing communication with the body's own tissues. In early human environments, this communication unfolded within a rich ecological web. Microorganisms were not simply invaders. Many were long-term companions. The gut, skin, and respiratory tract carried diverse microbial communities that coexisted with human cells. Over evolutionary time, these communities influenced how immune cells learned to respond. Exposure was not a single event, but a continuous conversation between host and environment. Within this conversation, immune tolerance developed alongside immune attack. Tolerance means recognizing what should not be destroyed. It is as important as the ability to eliminate pathogens. In environments where microbial diversity was broad and early exposure common, regulatory pathways had frequent opportunities to calibrate. Signals from commensal bacteria helped guide immune cells toward balanced responses. In contrast, modern environments characterized by reduced microbial diversity may shift the tone of this dialogue. Processed food, antibiotic overuse, limited outdoor contact, and urban living can alter the composition of the gut microbiome. Research across multiple populations shows that individuals living traditional lifestyles often possess greater microbial diversity compared to those in highly industrialized settings. Greater diversity is generally associated with more complex immune signaling, though the relationship is not simple or universally protective. The reduction in diversity does not guarantee illness, but it represents a change in baseline conditions. When microbial signals decrease or become less varied, immune regulation may respond differently. Some studies have observed associations between altered gut microbiota and increased rates of inflammatory conditions, including certain autoimmune disorders and allergies. These associations do not imply direct causation in every case. Genetic predisposition, environmental pollutants, diet composition, stress, and many other factors intersect. Still, the pattern suggests that the immune system evolved expecting regular microbial input. Beyond the gut, environmental biodiversity appears to influence immune balance. Contact with soil, plants, and animals exposes individuals to non-pathogenic microbes that may contribute to immune education. Urban environments often limit such exposure. Green spaces vary widely in microbial composition compared to natural ecosystems. The body, designed in landscapes filled with microbial signals, now inhabits spaces where those signals may be filtered or reduced. Another layer involves early childhood development. The first years of life represent a critical period for immune training. Mode of birth, breastfeeding, antibiotic exposure, and household environment all shape the initial microbial communities that colonize the infant gut. Modern medical practices have reduced many life-threatening infections, yet they also alter early microbial transmission. The long-term implications of these changes remain an active area of research. What emerges across these observations is not a simple accusation against cleanliness or medicine. Hygiene, vaccination, and antibiotics have saved millions of lives and remain essential. The deeper issue lies in balance. The immune system evolved within complex ecosystems. When those ecosystems become simplified, the regulatory framework may adjust in unexpected ways. Ease, in the form of sanitized and controlled environments, modifies the signals that once shaped immune calibration. The body continues to interpret its surroundings through mechanisms designed long ago. As microbial diversity narrows and exposure patterns shift, the immune system must navigate a landscape different from the one that formed it. Whether this altered landscape contributes to modern patterns of inflammatory disease remains a nuanced and evolving question, but the divergence itself is clear. When we step back and look across generations, another dimension of immune change becomes visible. The immune system does not operate in isolation from broader demographic patterns. As sanitation improves and infectious mortality declines, more individuals survive into adulthood and older age. This demographic success reshapes the immune landscape at the population level. In earlier eras, many immune challenges were acute and immediate. A child might encounter a pathogen and either recover or not survive. Those who survived often carried long-term immunity. The cycle was harsh, but it was direct. In modern contexts, vaccines prevent many severe infections, antibiotics treat others, and medical care reduces fatal outcomes. The immune system now confronts fewer life-threatening pathogens in some regions, yet it remains active across a longer lifespan. Longevity itself changes the context of immune function. As people live into later decades, the immune system must balance vigilance and restraint for far longer than in much of human history. Aging brings gradual changes in immune regulation. Certain responses become less robust, while background inflammation may increase subtly. This phenomenon, sometimes referred to in scientific literature as age-related immune modulation, reflects the cumulative effects of time rather than a sudden failure. In environments where caloric surplus, sedentary behavior, and chronic psychological stress are common, low-level inflammatory signaling may persist. Over decades, this persistent signaling can intersect with metabolic pathways and vascular systems in complex ways. Ease, in this sense, does not directly create disease but extends the duration over which regulatory imbalances can operate. Another layer involves medical intervention itself. Antibiotics are life-saving when used appropriately, yet repeated or unnecessary use can disrupt microbial communities that help modulate immunity. Modern healthcare systems must constantly balance immediate benefits against long-term ecological effects within the body. The immune system, shaped over millennia by exposure and recovery, now operates in partnership with pharmaceuticals and clinical protocols that did not exist during its evolutionary formation. This partnership has prevented immense suffering, but it also represents a novel biological context. Urban living further shapes immune exposure patterns across generations. Children raised in high-density, indoor-centered environments may encounter a different spectrum of microbes compared to those growing up in rural or nature-rich settings. Pollution, dietary patterns, and stress interact with immune function in subtle ways. The cumulative effect across decades may not be dramatic at any single moment, yet it contributes to changing patterns of allergic, inflammatory, and autoimmune conditions observed in certain populations. Importantly, these patterns are not uniform worldwide. Regions undergoing rapid industrialization often experience shifts in disease profiles as living conditions change. Infectious diseases may decline while chronic inflammatory conditions rise. This epidemiological transition reflects the broader theme of the entire discussion. As life becomes safer in some dimensions, the structure of illness reorganizes rather than disappears. The immune system remains fundamentally the same biological network shaped by ancient exposures. It continues to expect certain signals from the environment. When those signals change through sanitation, altered microbial diversity, extended lifespan, and medical intervention, the regulatory balance adjusts. The outcome is rarely immediate collapse. It is gradual recalibration within a new ecological framework. The deeper question lingers gently beneath the surface. If the immune system evolved through constant negotiation with a diverse and unpredictable world, how does it reinterpret safety, cleanliness, and longevity when those qualities become the dominant features of daily life? Energy, in the evolutionary landscape of early humans, was never abstract. It was immediate and embodied. Calories were gathered, hunted, dug from the ground, or carried over distance. Every unit of energy consumed required physical effort. This direct link between effort and intake shaped the metabolic system in precise ways. To understand why humans get sick when life gets easier, we must examine what happens when that link dissolves and energy becomes abundant without movement. The human body evolved under conditions where securing food demanded muscular work. Walking long distances, climbing, lifting, and persistent foraging meant that energy expenditure remained high. In such settings, the balance between intake and output was dynamic. When intake exceeded expenditure briefly, fat was stored as insurance against future scarcity. When intake dropped, stored fat was mobilized. Insulin, The hormone responsible for regulating blood glucose and promoting energy storage rose and fell in response to actual need. This oscillation was not a flaw, it was a finely tuned adaptation. The capacity to store fat efficiently was one of the most important survival traits in unpredictable environments. In periods of famine, individuals with greater fat reserves had a better chance of survival. Over many generations, genes that favored efficient storage persisted. This biological inheritance remains with us. The difficulty arises when environmental conditions change more rapidly than genetic adaptation. In industrial and post-industrial societies, calorie-dense foods are widely accessible. Many occupations no longer require sustained physical exertion. Transportation reduces the need for walking. Energy intake can exceed expenditure, not briefly, but chronically. The metabolic system, still designed for fluctuation, continues to respond as if scarcity might return. Insulin promotes storage. Adipose tissue expands. Signals that once served as short-term adjustments become persistent patterns. From a physiological perspective, the body does not immediately recognize chronic surplus as abnormal. It interprets repeated intake as preparation for potential deprivation. Yet deprivation rarely follows. Instead, meals arrive regularly, often rich in refined carbohydrates and fats that are quickly absorbed. Blood glucose levels rise more frequently. Insulin remains elevated for longer durations. Over time, tissues may become less responsive to insulin signals, a condition described in medical literature as insulin resistance. This development does not represent a sudden malfunction. It reflects prolonged exposure to signals that, in ancestral contexts, were transient. Excess energy also influences other systems. Adipose tissue is not inert storage. It secretes hormones and inflammatory mediators. In small amounts, these signals help regulate energy balance. In larger amounts, sustained over years, they may contribute to low-grade inflammation. The immune and metabolic systems intersect here, illustrating how energy surplus can ripple through multiple pathways. The shift from energy scarcity to persistent abundance represents one of the most profound environmental changes in human history. For hundreds of thousands of years, the metabolic system evolved under pressure to conserve and adapt to fluctuation. Within a few generations, many populations now experience sustained surplus combined with reduced physical necessity. The body continues to operate according to ancient logic. It stores when signaled. It prepares for famine that rarely comes. The tension between evolutionary expectation and modern constancy becomes especially visible in this domain of energy balance. The question deepens gently. If a system evolved to survive cycles of feast and famine, how does it respond when feast becomes the norm and famine disappears from daily life? In early human environments, energy storage was rarely separated from movement. The same muscles that hunted, gathered, carried, and built also acted as major regulators of glucose and fat metabolism. When muscles contract, they draw glucose from the bloodstream independently of insulin. In a landscape where walking and lifting were daily necessities, skeletal muscle served as a powerful stabilizer of blood sugar. After a meal, glucose was quickly used or stored in muscle tissue that would soon be called upon again. The metabolic system operated in coordination with physical demand. In modern settings, this coordination often weakens. Extended sitting reduces the frequency of muscle contraction. Even when total calorie intake remains similar, lower physical activity changes how the body handles energy. Glucose may circulate longer before being used. Insulin must work harder to signal uptake into tissues. Over time, reduced muscle engagement can contribute to decreased insulin sensitivity. This process is gradual. It unfolds across months and years rather than days. The body does not abruptly fail. It adapts to lower demand by altering signaling thresholds. Muscle tissue itself responds to use and disuse. In physically active populations, muscle mass remains relatively stable across adulthood. In sedentary contexts, muscle mass can decline earlier and more rapidly, a process influenced by both activity level and age. As muscle mass decreases, one of the body's primary sites for glucose disposal diminishes. This shifts more of the regulatory burden to other tissues, including the liver and adipose tissue. The liver, which once alternated between storing and releasing glucose based on fluctuating intake and effort, may now face continuous signals of abundance. In ancestral settings, fasting intervals allowed liver glycogen stores to empty and refill in cycles. In modern life, frequent meals and snacks can compress or eliminate these intervals. The liver remains metabolically active, yet its rhythm changes. Instead of switching cleanly between storage and release, it may operate in a prolonged storage mode. Another dimension involves appetite regulation. Hormones such as leptin and ghrelin evolved to signal energy sufficiency and hunger in environments where energy intake varied. Leptin, produced by adipose tissue, informs the brain about stored energy levels. In conditions of scarcity, declining leptin signaled the need to seek food. In persistent surplus, leptin levels rise, but the brain's response to this signal may diminish over time. This altered signaling can complicate appetite regulation. The system was designed to defend against weight loss more strongly than weight gain, because in evolutionary contexts, loss of stored energy posed a greater threat than moderate accumulation. Physical effort once provided a feedback loop. Energy expenditure influenced appetite and metabolic efficiency. In easier environments where effort is optional and food is engineered to be highly palatable, this feedback loop weakens. The brain's reward circuits may respond strongly to calorie-dense foods independent of physical need. The metabolic system, built for variability, now encounters constancy combined with stimulation. When examining this shift historically, the contrast becomes clear. For hundreds of thousands of years, muscle contraction, variable intake, and intermittent scarcity defined energy regulation. Within a short evolutionary window, energy intake can exceed expenditure with minimal physical necessity. The ancient logic of conservation persists inside a new landscape of abundance. The body continues to store, to signal hunger, to prepare for uncertainty even when uncertainty rarely interrupts supply. The deeper tension emerges quietly. When movement no longer anchors metabolism, how does a system designed for coordinated effort and intake recalibrate itself in an environment where energy flows freely but demand remains low? Beyond glucose and muscle, prolonged energy surplus influences the body at a more diffuse level. Adipose tissue, often thought of simply as stored fat, is biologically active. In early human contexts, moderate fat reserves acted as a buffer against famine, cold, and illness. The signals released from adipose tissue helped regulate appetite, reproduction, and immune responses. These signals were calibrated for relatively modest and fluctuating stores. When energy accumulation becomes sustained and extensive, adipose tissue expands not only in size but in function. Enlarged fat cells release a different pattern of chemical messengers, including hormones and inflammatory mediators. In small, transient amounts, these substances support immune vigilance and tissue repair. When present persistently over years, they can contribute to a subtle background level of inflammation, sometimes described as low-grade chronic inflammation. This state is not equivalent to acute infection. It is quieter and slower, but it intersects with vascular function, insulin signaling, and cellular repair. In ancestral settings, periods of energy surplus were typically followed by periods of depletion. Fat stores would rise and fall. In modern environments where depletion rarely arrives, expansion can continue gradually across decades. The body's regulatory systems attempt to compensate. Blood vessels adapt to higher nutrient flow. Pancreatic cells produce more insulin to manage repeated glucose surges. Immune cells interact with adipose tissue in new ways. These adaptations are not immediate breakdowns. They are efforts to maintain balance under sustained surplus. Another layer involves the distribution of fat. In evolutionary contexts, energy storage tended to accumulate subcutaneously, under the skin, where it posed fewer metabolic risks. Under prolonged surplus and low movement, fat may increasingly deposit around internal organs, a pattern associated in medical research with higher metabolic risk. This visceral fat is metabolically active and closely linked to inflammatory signaling. Again, this does not occur overnight. It reflects years of environmental constancy interacting with ancient storage mechanisms. Energy surplus also influences reproductive and developmental pathways. Adequate fat stores historically signaled sufficient resources for reproduction. In environments of abundance, these signals may appear earlier or remain persistently elevated. Puberty timing, fertility patterns, and hormonal cycles can shift in response to energy availability. The body interprets sustained abundance as a sign of environmental stability, even if that stability is artificial. Looking across evolutionary time, it becomes evident that the metabolic system was designed to guard against starvation more than against chronic excess. Starvation posed an immediate threat to survival and reproduction. Chronic excess, in the absence of mobility and fluctuation, rarely existed at scale. Thus, protective mechanisms against famine are robust and deeply ingrained. Mechanisms to defend against long-term overnutrition are comparatively less emphasized. The body continues to execute its ancient program: store when signaled, prepare for scarcity, maintain vigilance. Yet in a context where scarcity does not return, the protective strategy can create new forms of strain. The pattern is consistent with earlier transitions we have observed: ease, alters, signal, patterns. Signals guide regulation. Regulation shifts gradually in response. When abundance becomes constant and movement declines, metabolic and immune pathways intersect in ways that reflect evolutionary inheritance more than modern intention. The quiet question remains suspended. If a body evolved to survive cycles of shortage, what equilibrium does it seek in a world where shortage is rare and surplus endures? Long before cities and machines, the human nervous system evolved in open landscapes where danger was visible, immediate, and usually brief. A sudden movement in tall grass, the sound of an approaching storm, the tension of a rival group nearby, these were threats that demanded rapid response. The body answered with speed. Heart rate increased, breathing quickened, muscles tightened, stress hormones surged into the bloodstream, preparing for action. Yet once the threat passed, the body gradually returned to baseline. The stress response was designed to be intense but temporary. It was a system built for acute episodes rather than continuous activation. To understand why humans get sick when life gets easier, we must examine what happens when this ancient stress system operates in a new type of environment, one that is physically safer but psychologically dense. In early human settings, stress was closely tied to physical action. If danger appeared, movement followed. Running, climbing, fighting, or fleeing provided an outlet for the energy mobilized by stress hormones. After exertion, fatigue encouraged rest. The cycle of activation and recovery completed itself. The nervous system oscillated between alertness and calm. Nightfall brought darkness and relative quiet. Social bonds within small groups provided reassurance and shared vigilance. In many modern environments, immediate physical threats are far less common, yet psychological stresses have multiplied. Financial uncertainty, work deadlines, social comparison, constant information flow, and digital notifications create a background of cognitive stimulation. These signals do not resemble a predator in the grass, but they can activate overlapping biological pathways. The hypothalamic pituitary adrenal axis, central to the stress response, responds to perceived threats whether they are physical or abstract. Cortisol is released, blood pressure rises, attention narrows. The difference lies in duration and resolution. Modern stressors often lack a clear endpoint. A message unanswered, a news headline, a long-term financial concern, these can linger for days or weeks. Physical action may not accompany them. The body prepares for exertion that does not occur. Over time, repeated or prolonged activation without full recovery can alter baseline regulation. This does not imply that modern life is inherently damaging. The nervous system is adaptable. Short-term stress can enhance focus and performance. However, when activation becomes chronic and recovery insufficient, the balance between sympathetic arousal and parasympathetic restoration may shift. Sleep, appetite, and immune function can all be influenced by sustained stress signaling. From an evolutionary perspective, the stress response was calibrated for environments where threats were concrete and episodic. The safety provided by modern infrastructure reduces many immediate dangers: predation, starvation, exposure to extreme weather. Yet the brain, shaped in unpredictable settings, continues to scan for risk. In environments saturated with information and social evaluation, it may interpret ambiguity as threat. The body cannot easily distinguish between a physical predator and a prolonged abstract concern. Ease, therefore, does not eliminate stress. It transforms its character. Physical danger recedes while psychological pressure expands. The nervous system, still organized around rapid mobilization and recovery, must navigate a landscape where mobilization is frequent but recovery is fragmented. The question gently returns: if the stress system evolved for short bursts of survival-driven urgency, how does it adapt when urgency becomes a background condition rather than an exception? In early human life, stress rarely existed without context. It was embedded within physical reality. A predator approached, a storm gathered, a conflict erupted. The body responded with precision because the threat was tangible. Once resolved, the environment itself signaled safety. Silence returned. Darkness deepened. Companions gathered close. These sensory cues, stillness, warmth, shared presence, helped deactivate the stress response. The nervous system was guided not only by danger but by unmistakable signals of relief. In many modern settings, these sensory transitions are less distinct. Artificial light extends activity into hours once reserved for rest. Digital devices emit a steady stream of information regardless of time or location. Social interaction can occur continuously through screens, dissolving clear boundaries between work, community, and solitude. The nervous system, shaped in cycles of daylight and darkness, movement and stillness, now receives mixed signals. Evening may resemble day in brightness. Work may extend into spaces once associated with recovery. The cues that once marked the end of stress are blurred. Sleep is particularly sensitive to this shift. The circadian system coordinates hormonal patterns that prepare the body for rest. In ancestral environments, the absence of artificial light and the physical fatigue of daily movement encourage deeper sleep cycles. Modern lighting and prolonged mental engagement can delay the onset of sleep and reduce its quality. When sleep shortens or fragments, cortisol regulation may shift. The body becomes more reactive to stressors. Appetite hormones can fluctuate. Immune responses may alter. The effects are gradual, but they accumulate over years. Another element involves social scale. Early human groups were small and stable. Individuals typically interacted with a limited number of familiar faces. Social evaluation occurred within close-knit communities where reputation and cooperation were visible and immediate. In contemporary societies, social exposure extends far beyond local groups. Through media and digital networks, individuals compare themselves to vast numbers of others. Social approval and criticism can arrive instantly and from distant sources. The brain's social circuitry, evolved for intimate groups, now processes signals from far larger audiences. This expansion can amplify perceived social stress. The body's stress pathways do not differentiate sharply between a critical comment from a nearby group member and widespread digital scrutiny. Both can activate similar biological responses. Over time, repeated social evaluation may contribute to persistent low-level arousal. Physical safety does not fully translate into neurological calm. Even in secure environments, the mind may remain vigilant. In early landscapes, vigilance often had a clear focus. A sound in the bushes required attention. In modern contexts, vigilance can become diffuse. The mind scans emails, headlines, and social signals without a clear endpoint. The nervous system remains engaged, but without the physical resolution that once followed activation. This shift does not imply that modern life is uniformly harmful. It reflects a change in signal clarity. The body evolved to move between unmistakable states of alertness and rest. When those states blend into one another, regulation becomes more complex. Ease in terms of physical safety coexists with cognitive stimulation that rarely ceases. The deeper pattern echoes earlier themes. Biological systems calibrated for rhythmic fluctuation encounter environments where fluctuation flattens or extends. If recovery cues grow faint while stimulation remains constant, how does the stress response recalibrate across decades of modern living? When stress becomes less tied to immediate physical threat and more connected to ongoing mental interpretation, its physiological pattern can subtly change. In ancestral settings, stress responses were often synchronized with action. Muscles contracted. Energy was expended. After the event, exhaustion signaled the nervous system to shift toward recovery. In modern contexts, stress may arise while the body remains physically still. A person can experience heightened alertness while sitting in a chair, staring at a screen, or lying awake at night. The biological signals are familiar elevated heart rate, cortisol release, increased glucose availability, but the outlet for those signals is limited. Over time, this mismatch between activation and movement may influence how stress hormones circulate. Cortisol follows a daily rhythm, rising in the morning and declining toward evening. Persistent psychological stress, irregular sleep, and late-night light exposure can flatten or shift this rhythm. When cortisol remains elevated beyond its intended window, it can interact with metabolic pathways, influencing appetite and fat storage. The same hormone that once mobilized energy for a brief escape may now contribute to sustained metabolic signaling in the absence of physical exertion. The immune system also responds to stress hormones. Short bursts of stress can temporarily enhance certain immune functions. Chronic elevation, however, may dysregulate inflammatory responses. The boundary between nervous and immune systems becomes less distinct. Signals originally meant to coordinate rapid defense now circulate within a context of prolonged anticipation. In early human environments, anticipation usually concerned near-term events, weather shifts, migration decisions, immediate social tension. In modern life, anticipation can extend far into the future. Financial planning, career uncertainty, global events, and personal comparison create cognitive projections that stretch months or years ahead. The brain's capacity for foresight and adaptive strength interacts with a stress system not originally designed for extended abstract forecasting. The body responds to imagined scenarios in ways similar to immediate threats. This prolonged cognitive engagement may maintain subtle physiological arousal. Social isolation can compound this effect. Although urban environments are densely populated, individuals may experience less consistent face-to-face bonding than in small ancestral groups. Social support historically played a role in buffering stress responses. Shared vigilance, reduced individual burden. In fragmented communities, stress may be carried more privately. The nervous system, lacking clear signals of collective safety, may remain more reactive. None of these processes imply inevitability of illness. The stress system is flexible and capable of adaptation. Many individuals thrive in modern environments. The concern lies in cumulative exposure. Decades of altered sleep patterns, sustained psychological vigilance, limited physical resolution of stress, and fluctuating social support may gradually shape baseline regulation. The body does not collapse under ease, it recalibrates within it. The recalibration reflects ancient circuitry navigating a novel environment. When physical safety improves but mental stimulation intensifies, the stress response may operate in patterns unfamiliar to its evolutionary origins. The question remains open and quiet. If the human nervous system evolved for cycles of visible danger and clear recovery, what equilibrium does it seek in a world where danger is abstract and recovery cues are often muted? For most of human history, reaching old age was uncertain. Many individuals died from infection, injury, childbirth complications, or environmental hardship long before the later decades of life. Those who survived into older age were often the exception rather than the norm. The human body, as it evolved across hundreds of thousands of years, was primarily shaped by pressures that influenced survival and reproduction in early and middle adulthood. To understand why humans get sick when life gets easier, we must consider what happens when lifespan extends far beyond the conditions that originally defined biological success. Natural selection favors traits that enhance the likelihood of passing genes to the next generation. Traits that exert their strongest effects after reproductive years are subject to weaker selective pressure. This does not mean the body was designed to fail in later life, but it does mean that many maintenance processes were optimized for earlier stages of survival. In ancestral settings, the average lifespan was shorter, though it varied widely. Some individuals lived into their 60s or beyond, yet the proportion of the population reaching advanced age was smaller than in many modern societies. With improvements in sanitation, nutrition, and medical care, life expectancy has increased dramatically in numerous regions. More individuals now live into their 70s, 80s, and beyond. The body's repair systems, DNA repair, protein turnover, immune surveillance continue to operate throughout life. yet they were calibrated within a context where long-term exposure to constant abundance, sedentary behavior, and persistent psychological stress did not exist at scale. As decades accumulate, small imbalances can compound. Metabolic shifts that might have been tolerable for a shorter lifespan become more consequential over extended years. Low-grade inflammation that once resolved quickly may linger. Vascular systems experience prolonged exposure to elevated blood glucose or blood pressure. Joints bear the weight of reduced muscle support. The extension of lifespan does not automatically create disease. It reveals the long-term consequences of environmental conditions interacting with biological design. Another factor involves cellular aging. Cells replicate and repair themselves continually, but replication is not infinite. Telomeres, protective caps at the ends of chromosomes, gradually shorten with repeated cell division. Oxidative stress and inflammation can accelerate certain aspects of cellular wear. In ancestral environments, individuals may not have lived long enough for some of these processes to dominate health outcomes. In modern contexts, extended lifespan allows age-related changes to emerge more prominently. Ease, in the form of reduced early mortality, shifts the burden of disease toward later decades. Chronic conditions associated with aging cardiovascular disease, certain cancers, neurodegenerative disorders become more visible not because the body has changed fundamentally, but because it endures longer within altered environments. The interaction between longevity and modern lifestyle deepens the mismatch discussed throughout this exploration. The body was shaped under pressures of survival and reproduction in unpredictable landscapes. It now operates across extended decades within stable, calorie-rich, technologically dense settings. The biological systems that once balanced acute threats must now maintain equilibrium over prolonged time spans. The question emerges gently. When human life extends far beyond the evolutionary horizon that shaped its design, how do ancient repair mechanisms cope with decades of relative ease and environmental constancy? As lifespan extends, the body is asked to perform a task that was comparatively rare across much of human evolution, maintaining internal balance across many decades of environmental constancy. In early landscapes, survival into older age certainly occurred, but it unfolded within a rhythm of physical movement, variable diet, and intermittent hardship. Aging did not happen in climate-controlled rooms with continuous caloric supply and minimal muscular demand. It occurred in bodies that were used daily, and in environments that required constant adaptation. When aging unfolds in a modern context of relative ease, its expression may change. Over time, tissues accumulate small injuries, proteins misfold, cells experience oxidative stress. Under conditions of regular physical activity and dietary variability, many of these changes are met with repair signals. Exercise stimulates mitochondrial renewal. Fasting intervals can influence metabolic pathways related to cellular maintenance. Sleep aligned with natural light-dark cycles supports hormone regulation. When these stimuli decline, the signals that coordinate repair may also shift. The result is not immediate dysfunction but gradual alteration in resilience. Aging becomes not only a matter of years lived, but of environmental input across those years. Another element concerns muscle and bone. In ancestral settings, daily life demanded loading of the skeleton. Carrying weight, walking on uneven ground, and lifting objects stimulated bone remodeling. Muscle contractions provided continuous mechanical feedback. In later life, this feedback helped maintain strength and balance. In sedentary environments, especially as individuals age, muscle mass can decline more rapidly. Bone density may decrease in the absence of regular loading. These changes increase vulnerability to frailty and injury. The body, designed for persistent engagement with gravity and terrain, adapts to reduced demand by conserving resources. Yet this conservation can reduce reserve capacity in advanced age. Metabolic changes also intersect with aging. Insulin sensitivity often declines gradually over time. In contexts of caloric surplus and reduced movement, this decline may accelerate. The same hormonal systems that once shifted flexibly between feast and famine now operate within steady abundance. Over decades, repeated exposure to elevated glucose and insulin can influence vascular integrity and organ function. Again, this is not a sudden breakdown but a slow accumulation of small shifts. The immune system, discussed earlier, also changes with age. Some components become less responsive, while background inflammatory signals may increase. This age-related modulation reflects both intrinsic cellular aging and cumulative environmental exposure. In earlier human contexts, older individuals often continued to move, gather, and contribute socially within their groups. Physical engagement did not end abruptly at a certain age. In modern life, retirement from physical labor and increased sedentary behavior can further reduce stimuli that once supported resilience. Longevity itself becomes a new environmental condition. The body, still structured by ancient design, must maintain equilibrium across unprecedented spans of time under relatively stable and often comfortable conditions. Ease reduces certain immediate dangers but lengthens exposure to subtle imbalances. The deeper pattern reappears. Systems shaped in fluctuating environments are now asked to sustain balance across prolonged uniformity. If aging unfolds within a world that differs fundamentally from the one in which human biology was formed, how does that difference shape the way health and disease emerge across the later decades of life? As longevity increases across populations, aging becomes not only a biological process but a social and environmental condition. Entire communities now include large proportions of individuals living into advanced age. This demographic shift alters daily structure, healthcare systems, and intergenerational dynamics. In earlier human groups, elders often remained embedded within physically active routines, contributing knowledge, childcare, and light labor according to capacity. Their movement patterns changed with age, yet rarely ceased entirely. In contrast, many modern societies separate older adults from physically demanding tasks and, at times, from sustained social engagement. The body, shaped by lifelong participation in shared survival, may experience aging differently when activity and social integration diminish simultaneously. Over decades of relative ease, cumulative exposure to environmental constancy becomes visible. Continuous access to calorie-dense food, reduced mechanical loading of bones and muscles, and prolonged psychological stress interact with the intrinsic processes of cellular aging. Telomere shortening, mitochondrial decline, and altered protein regulation unfold gradually in all humans. Yet the pace and expression of these changes are influenced by environmental signals. Physical activity can stimulate mitochondrial biogenesis. Social connection can buffer stress responses. Nutritional patterns affect metabolic regulation. When ease reduces some of these stimuli, the trajectory of aging may subtly shift. It is important to note that aging itself is not a disease. It is a natural biological progression shaped by evolutionary priorities that emphasized early survival and reproduction. However, the extension of lifespan means that age-related conditions, cardiovascular disease, metabolic disorders, neurodegenerative changes occupy a larger portion of life. In ancestral contexts, fewer individuals lived long enough for these conditions to dominate population health patterns. Modern medicine allows survival through acute illness, revealing the longer arc of chronic change. Another dimension involves repair capacity. The body constantly balances damage and renewal. Cells accumulate molecular errors, but repair enzymes correct many of them. Over time, repair efficiency may decline. In environments of sustained metabolic surplus and reduced physical challenge, oxidative stress and inflammatory signaling may increase modestly, adding to the burden on repair systems. This does not imply inevitability, rather, it reflects interaction between intrinsic aging mechanisms and external conditions. The human body was not designed for a specific expiration date, yet it was calibrated in a world where fewer decades were typical. Longevity in modern societies is an extraordinary achievement. It represents improved survival, sanitation, and healthcare. At the same time, it introduces a prolonged phase during which ancient biological systems must maintain stability in a novel context. Ease reduces early mortality and physical hardship, but it extends exposure to environmental patterns that differ from those under which the body evolved. The essential pattern remains consistent with earlier themes. When life becomes safer and longer, disease does not disappear. It reorganizes. The aging body becomes a mirror reflecting both evolutionary inheritance and modern environment. The question that lingers quietly is this: as humans live longer than ever before within conditions of sustained comfort, How will ancient repair systems continue to negotiate the balance between endurance and decline across the extended arc of life? When we widen the lens from individual biology to population structure, another quiet transformation appears. Human groups today are organized very differently from those that shaped most of our evolutionary history. For hundreds of thousands of years, humans lived in relatively small bands composed of multiple generations. Children grew up surrounded not only by parents but by grandparents, siblings, and unrelated adults. Knowledge moved orally. Daily survival tasks were shared. Illness, injury, and aging unfolded within tight social networks. To understand why humans get sick when life gets easier, we must consider how these structural shifts in population and social organization influence health across generations. In early human settings, population density was low, groups were mobile, resource distribution limited size. Social roles were flexible. Cooperation was essential because survival depended on shared effort. This structure influenced stress regulation, childcare, and even metabolic patterns. Infants were often carried, breastfed for extended periods, and exposed to constant human contact. Social buffering reduced individual stress load. When danger appeared, vigilance was collective rather than solitary. In modern societies, population density is paradoxical. Cities hold millions of individuals, yet social networks can be fragmented. Families are smaller. Many households include only one or two generations. Urban life may reduce daily contact with extended kin. The structure of care changes. Elderly individuals may live separately from younger generations. Children may spend large portions of their day in institutional settings. These arrangements are not inherently harmful, but they represent a shift from ancestral patterns. Social connection influences physiology. Studies in psychology and public health have repeatedly observed associations between social isolation and increased risk of various health outcomes, including cardiovascular disease and depression. The mechanisms are complex and involve stress hormones, inflammatory signaling, and behavioral factors. In small ancestral groups, social bonds were reinforced by shared labor and proximity. Modern social structures, shaped by mobility and economic specialization, sometimes weaken continuous physical presence. Digital communication can maintain connection across distance, yet it does not fully replicate embodied interaction. Demographic transition also alters reproductive patterns. In many industrialized societies, families have fewer children. Age at first, childbirth increases. Lifespan extends. As a result, population pyramids invert. A larger proportion of individuals are older. This shift influences healthcare demands and disease prevalence. Chronic illnesses associated with aging become more common not solely because bodies fail, but because more bodies survive into later decades. Ease in terms of child survival and life expectancy reshapes the health profile of entire societies. Another generational layer involves early life exposure. In small, mobile groups, infants were immersed in varied environments from birth, soil, animals, fluctuating temperatures, constant touch. In modern contexts, early life may be more controlled and sanitized. Educational systems and indoor lifestyles structure childhood differently. These differences may influence immune calibration, stress resilience, and metabolic development in subtle ways that unfold across decades. When population structure shifts, biological systems do not change instantly. They continue to operate according to ancient principles within new social arrangements. Extended lifespan, smaller families, urban concentration, and institutionalized care create a landscape unfamiliar to our evolutionary past. Health patterns reflect this landscape. The body, still shaped by small group living and shared survival, navigates societies built around specialization and scale. The question that begins to form is not whether modern social organization is superior or inferior, but how ancient physiological systems respond when the structure of human community changes so profoundly across only a few generations. As population structures shift, the flow of experience across generations changes as well. In small ancestral groups, knowledge about food, healing practices, seasonal patterns, and social norms was transmitted through daily observation and participation. Children watched adults gather, cook, repair tools, and care for the elderly. Learning was embodied and continuous. The environment itself acted as a teacher, shaping habits from early childhood. In modern societies, education often moves into formal institutions separated from daily subsistence. Children spend many hours indoors, guided by abstract curricula. This shift has brought literacy, scientific understanding, and technological skill, yet it also reduces direct contact with the ecological rhythms that once structured development. From a biological perspective, early childhood is a sensitive period. Metabolic pathways, stress responses, and immune regulation are particularly plastic. Nutrition, sleep patterns, physical activity, and social attachment during these years influence long-term trajectories. In ancestral settings, children were typically physically active throughout the day. Play occurred outdoors. Movement patterns varied naturally: running, climbing, balancing. Food intake reflected seasonal availability and group sharing. In contrast, modern childhood may involve prolonged sitting, structured schedules, and exposure to highly processed foods. These patterns do not guarantee illness, but they represent environmental inputs different from those that shaped early human development. Another dimension involves generational continuity of lifestyle. In mobile bands, adults and elders modeled the same survival skills they practiced in youth. Movement remained integrated into life across decades. In industrial and post-industrial contexts, work and leisure patterns may change dramatically between generations. Technological advances alter occupations rapidly. A grandparent's daily routine may bear little resemblance to that of a grandchild. This discontinuity can influence shared habits around diet, activity, and sleep. Cultural transmission continues, yet it unfolds within an environment where technological change outpaces generational memory. Demographic aging further alters intergenerational balance. In many countries, a smaller working-age population supports a growing elderly population. Healthcare systems adapt to manage chronic conditions over longer spans. Family structures shift to accommodate caregiving roles. Ease in the form of medical advancement extends life, yet it also increases the duration of dependency for some individuals. The physiological consequences of prolonged sedentary care, institutional living, or reduced autonomy may intersect with aging processes discussed earlier. Urbanization intensifies these trends. In densely populated cities, green space and natural terrain may be limited. Access to varied outdoor environments becomes uneven across socioeconomic lines. Children and older adults alike may spend large portions of their day indoors. The body, evolved for interaction with varied landscapes, adjusts to built environments characterized by flat surfaces and artificial lighting. Across generations, these patterns accumulate. The concept of normal childhood, adulthood, and old age shifts within a few decades. Biological systems shaped across millennia must interpret this rapid transformation. The continuity that once existed between environment, daily activity, and generational learning becomes fragmented. Ease, in the form of structured institutions and technological convenience, reorganizes how experience flows from one generation to the next. The underlying question continues to echo softly. When human development unfolds within environments that differ fundamentally from those that shaped our species, how do these differences influence health patterns not just within individuals, but across entire generations? When we observe entire populations across decades, patterns begin to emerge that are difficult to see at the level of a single individual. Health is not only a matter of personal behavior or isolated biology, it is shaped by the structure of societies and the timing of generational change. In ancestral human groups, environmental conditions shifted slowly. Climate varied, food availability changed seasonally, but the underlying structure of daily life remained relatively stable across many generations. A child's adulthood often resembled the adulthood of parents and grandparents in its basic demands: movement, shared labor, direct engagement with land and weather. The body developed within a predictable ecological rhythm. In contrast, modern societies experience rapid transformation. Within a single lifetime, transportation, communication, food production, and occupational structure can change dramatically. A grandparent born into a rural agricultural setting may witness the rise of urban living, digital technology, and processed food systems within decades. This compression of change means that biological systems calibrated in one context are suddenly exposed to another. The mismatch discussed throughout this exploration is not static. It intensifies when change accelerates. Generational studies in public health show that rates of certain chronic conditions can shift significantly within a few decades as societies industrialize or urbanize. When populations move from physically demanding, food-scarce environments to sedentary, calorie-rich settings, patterns of metabolic disease often rise. These transitions are not explained solely by genetics, because genetic change unfolds slowly. They reflect interaction between inherited biology and altered environments. The body remains largely the same, the surroundings transform. Another generational factor involves epigenetics, the way environmental signals can influence gene expression without altering the DNA sequence itself. Nutritional status, stress exposure, and early life conditions can leave molecular marks that shape how genes are expressed. Some of these marks may persist into subsequent generations. Research in this area continues to evolve, and the mechanisms are complex, but it suggests that the effects of environmental change can ripple beyond one lifetime. When ease alters diet, stress patterns, or microbial exposure, the consequences may influence not only individuals but their descendants. Social inequality also shapes generational health. Access to nutritious food, safe housing, education, and healthcare varies widely within and between societies. Ease is unevenly distributed. Some groups experience both technological convenience and sustained stress due to economic instability or discrimination. These layered exposures can compound biological strain across generations. The concept of health becomes intertwined with social structure. Across evolutionary time, human biology developed within small, relatively egalitarian groups where survival was interdependent. In modern large-scale societies, disparities can widen. When examining population trends, a recurring pattern appears. As life becomes easier in terms of reduced infectious mortality and technological convenience, chronic diseases increase in prominence. This does not imply that ease causes disease in a simple sense. It reveals that the configuration of risk shifts with social organization. The body continues to operate according to ancient principles while navigating rapid generational transformation. The deeper question remains open. When societies evolve faster than the biology they contain, how will successive generations negotiate the widening distance between inherited design and modern environment? When we gather the threads of movement, metabolism, immunity, stress, aging, and generational change, a quiet pattern becomes visible. Across hundreds of thousands of years, the human body evolved within fluctuating environments defined by variability. Food availability changed, temperature shifted, physical effort was unavoidable. Social bonds were close and immediate. Microbial exposure was diverse. Threats were acute and visible. The body's systems, metabolic, immune, nervous, and structural, were shaped in response to these signals. Regulation depended on rhythm, strain followed by recovery, scarcity followed by intake, danger followed by calm. In the modern world, many of these rhythms flatten. Temperature remains constant indoors. Food is accessible throughout the day. Physical effort becomes optional. Artificial light blurs day and night. Psychological stress persists without clear resolution. Longevity extends far beyond earlier norms. Social structures fragment or expand beyond intimate scale. None of these changes are inherently harmful. Many represent extraordinary achievements in human history, yet each modifies the signals that once guided biological calibration. The concept that quietly emerges is not that comfort is wrong, but that biological systems respond to patterns. When patterns shift abruptly or become uniform, regulation adjusts. In evolutionary biology, this idea is often described as a mismatch between ancestral environment and contemporary conditions. The mismatch is not a moral judgment, it is a temporal observation. The genes that influence insulin sensitivity, inflammatory response, stress reactivity, and appetite were selected in landscapes very different from climate-controlled cities. When the external environment changes faster than genetic adaptation, tension can arise between expectation and reality. This tension does not create disease instantly. It alters baseline states, slight elevations in inflammatory signaling, subtle shifts in hormone timing, gradual changes in muscle mass and bone density, minor alterations in microbial diversity. Over years and decades, these small adjustments can intersect, amplifying one another. Chronic conditions emerge not as singular failures, but as outcomes of sustained divergence between design and context. From an archaeological viewpoint, human remains tell a story of adaptation to hardship. From epidemiological data, modern statistics reveal patterns of chronic disease rising alongside industrialization and urbanization. From cellular biology, we see repair systems designed for dynamic input rather than constancy. Each perspective converges on the same theme. The body was shaped under conditions of variability and intermittent challenge. Ease reduces certain dangers, but may also reduce the variability that once maintained resilience. Importantly, this recognition does not call for romanticizing hardship or rejecting progress. It invites careful reflection on how modern environments can better align with biological inheritance. Small reintroductions of rhythm movement, exposure to natural light, social connection, varied diet may serve not as a return to the past, but as a bridge between ancient design and contemporary life. The central question remains unresolved, as it must. If humans have engineered a world of unprecedented safety and stability, how can the body, forged in uncertainty and fluctuation, find equilibrium within this new and easier landscape? When we consider the idea of mismatch more closely, it becomes less a theory of blame and more a framework of timing. The human body is not defective, it is deeply competent within the context that shaped it. The metabolic system conserves energy because scarcity once threatened survival. The immune system reacts strongly because infection once carried immediate danger. The stress response mobilizes quickly because hesitation could cost a life. Each of these systems reflects intelligence forged in uncertain landscapes. The difficulty arises when the context shifts faster than the system can recalibrate. In a world where calories are continuously available, conservation mechanisms may promote accumulation. In environments where microbial exposure narrows, immune regulation may interpret signals differently. In societies where psychological vigilance persists without physical resolution, stress pathways may operate without clear recovery cues. The body continues to follow its ancient instructions, even when the environment no longer matches the assumptions embedded in those instructions. This perspective reframes modern chronic illness not as a moral failing or a simple consequence of individual weakness, but as an emergent property of rapid environmental change. Over centuries, and especially over recent decades, technology has transformed how humans move, eat, sleep, connect, and age. These transformations unfolded within a fraction of evolutionary time. Genetic adaptation, by contrast, proceeds gradually. Most of the genes influencing metabolism, immunity, and stress regulation are largely the same as they were thousands of years ago. The body still expects fluctuation, effort, and exposure. It still prepares for scarcity, even when abundance persists. From a historical viewpoint, this is not the first time humans have altered their environment. The adoption of agriculture, the rise of cities, and the spread of industry each introduce new pressures. Yet the scale and speed of contemporary change are unprecedented. Digital connectivity, global food systems, artificial light, and climate control compress variation into stability. The biological question becomes subtle. What happens when the signals guiding regulation become uniform rather than dynamic? Biological systems thrive on feedback. Muscles strengthen in response to load. Bones remodel in response to impact. Metabolic pathways adjust to shifts in intake. The immune system calibrates through exposure and resolution. When feedback diminishes or becomes constant, systems may lose some of their adaptive sharpness. This does not guarantee illness, but it may increase vulnerability over time. It suggests that the health challenges of modern societies may reflect not only excess, but the reduction of meaningful variability. The recognition of mismatch invites humility. It reminds us that technological progress and biological inheritance operate on different clocks. It encourages attention to patterns rather than isolated factors. Movement, light, social contact, microbial diversity, and energy fluctuation are not relics of a primitive past. They are components of the environment that shaped our physiology. The question that emerges at this stage is not whether comfort is inherently harmful, but how comfort can coexist with the rhythms the body still expects. If ancient regulatory systems continue to operate within us, what forms of modern living might help restore dialogue between inherited design and contemporary ease? If we return to the central question, why humans get sick when life gets easier, the answer does not rest in a single organ, a single nutrient, or a single behavior. It rests in time. For hundreds of thousands of years, the human body learned to interpret a world defined by fluctuation. Energy rose and fell. Light followed the sun. Movement was inseparable from survival. Microbial exposure was constant but varied. Stress arrived suddenly and resolved through action. Aging unfolded within physically engaged communities. These patterns did not guarantee health in the modern sense, but they created coherence between environment and physiology. In the span of a few centuries, and especially within the last few decades, that coherence shifted. Food became constant, movement optional, light extended into the night. Psychological vigilance replaced many physical threats. Longevity expanded far beyond earlier norms. Microbial landscapes narrowed. Social structures reorganized. Each change improved safety or comfort in measurable ways. Yet each also modified the signals that once guided biological calibration. The body did not redesign itself during this transition. It continues to operate with metabolic pathways tuned for scarcity, immune networks shaped by diverse exposure, and stress systems built for acute resolution. When these systems encounter sustained abundance, reduced variability, and prolonged psychological stimulation, regulation may drift. Illness in this context is rarely an immediate collapse. It is often the cumulative outcome of small adjustments unfolding across years. Low-grade inflammation persists. Insulin sensitivity shifts. Sleep patterns fragment. Muscle mass declines. None of these changes are dramatic at first. They become visible when extended across decades. Recognizing this pattern invites a different response than fear or nostalgia. It suggests that health in an easy world may depend on reintroducing certain rhythms rather than rejecting progress. Regular movement restores dialogue between muscle and metabolism. Exposure to natural light reinforces circadian timing. Social connection buffers stress responses. Varied, minimally processed foods support metabolic flexibility. Contact with diverse environments influences immune balance. These are not returns to a distant past, but deliberate alignments between ancient biology and modern context. The human story is one of adaptation. We reshaped landscapes, built cities, developed medicine, and extended life. The next stage of adaptation may involve learning how to live within our own inventions without losing the rhythms that shaped us. The body does not demand hardship for its own sake. It responds to pattern, variation, and engagement. As we rest tonight in climate-controlled rooms, under artificial light, with food stored nearby, the deeper question lingers quietly beneath the comfort. In a world we have made safer and easier than ever before, how can we help an ancient body remember the rhythms it was built to follow?